Hello students, in this video I'll cover the syllabus of infinite series, in which I'll cover that uniform convergence of series and its properties. This is the syllabus of BSc 4th semester infinite series chapter, Karnataka University, Dharwad. So in which we'll start with a series of functions. Before we'd like to give a concepts of uniform convergence of series. So we extend our concept of infinite series to include the possibility that each term un may be a function of some variable un of x. The partial sums becomes functions of the variable x. It means Sn of x is equal to partial sums of the terms u1 of x plus u2 of x and so on plus un of x, as does the series sum, which defined as the limit of the partial sums. Limit of the un of x means what? That is the limit of Sn of x. As n approaches to infinity, it is summation of un of x as n running from 1 to infinity. It means what? Function of x, that is s of x. So far we have concerned ourselves with the behavior of partial sums as a function of n. Now we consider how the foregoing quantities depend on x. The key concept here is that the uniform is of uniform convergence. Now let us see that concepts of uniform convergence. If for any small epsilon is positive, there exists a number n which is independent of x in the interval closed interval ab, such that that's modulus of s of x minus Sn of x is less than epsilon for all small n is greater than or equal to capital N. That means this partial sums of the function s of x minus, so summation of partial sums of the terms Sn of x, n terms of x there. So which distance is very close to each other for n is greater than or equal to capital N. Then the series is said to be uniformly convergent in the interval closed interval AB. This says that for our series to be uniformly convergent, it must be possible to find finite n, so that the absolute value of the tail of the infinite series, that is summation of ui of x, where I is behind n, that means n plus 1 to infinity, will be less than an arbitrary small value epsilon that for all x in the given interval closed interval AB, including the endpoints, means as we know that it is the closed interval AB. It means what? This partial sums of that summation of ui of x, that is I is running from after n, that is n plus 1 to infinity, will be less than epsilon. However, epsilon is very small for all the values of x in the given closed interval. So then we can say that it is the uniformly convergence in the given interval AB. That. What is non-uniform convergence? Now we consider the interval 0 and 1, closed interval 0 and 1. The series, the function of s of x, we consider that is the one series here, that is 1 minus x into x power n, as n is running from 0 to infinity. As we know that it is for closed interval 0 and 1, the geometric series as nature of the geometric series is convergent, that is summation of x power n, with the value of 1 by 1 minus x, as we know that as that. So s of x is 1 for these values of x. But at x equal to 1, every term of the series will become a 0, and therefore s of 1 is 0. That is summation of 1 minus x power n as n running from 0 to infinity, it is 1 for the closed interval 0 to 1. Behind that means x equal to 1 only, that is that summation of 1 minus x into x power n is 0 to infinity, this series is 0 that. So s of x is convergent for the entire interval closed interval 0, 1, and because each term is non-negative, it is also called that is absolutely convergent. If x is not equal to 0, this is a series for which the partial sum Sn is 1 minus x power n, as can be seen by comparison test with the given equation 3. Since s of x is 1, the uniform convergence criterion is, that is modulus of 1 minus x power n. That is, as we know that 1 gets cancelled, it is xn. That means power of that n of x is less than epsilon. No matter what the values of capital N and a sufficiently small epsilon may be, there will be an x value which is close to 1 where this criterion is violated. The underlying problem is that x equal to 1 is the convergence limit of the geometric series, and it is not possible to have a convergence rate that is bounded independently of x in the range which includes x equal to 1. Also, we note from this example that absolute and uniform convergence are independent concepts, as we know that. The series in this example has absolute but not uniform convergence. We will shortly present examples of series that are uniformly but only conditionally convergent, as we know in the previous videos. And there are series that have neither or both of these properties. So that is what that. So as we know that already, it is the partial sum, that is an let a1 of x plus a2 of x plus a3 of x and so on an of x be an infinite series, each of which is defined in the open interval ab. Let Sn of x be the sum of its first n terms, that is n term you can take, that is Sn of x. At the end x equal to x1, so if limit Sn of x1 equal to s of x1, so that as n running from n approaches to infinity, then we can say that this series summation an of x is said to sum Sn of x1 at that point. Now we can see, as already we have seen that definition of uniform convergence. Again recall that definition of uniformly convergent series. The series an of x is said to be uniformly convergent in the given interval, open interval ab, for a given epsilon greater than 0. There exists a number capital N that should be also positive, that can be found independent of x, such that for every value of x in the interval open interval ab, such that so difference of s of x and Sn of x, which are very close to each other, for all n should be greater than n, capital N, means what? Modulus of s of x minus Sn of x less than epsilon, for all n should be greater than n. So now we shall see that one important test for these uniform convergence series. So the most commonly encountered test for uniform convergence is the Weierstrass M test. If we can construct a series of numbers, summation of mi, where I is running from 1 to infinity, in which those terms mi is greater than or equal to modulus of ui of x for all x in the interval closed interval ab, and also this summation of mi, I is running from 1 to infinity, is convergence, our series ui will be uniformly convergent in the given closed interval AB. That means, again I will state this Weierstrass-M test. A series of functions summation un will be converged uniformly or will be converged absolutely and also absolutely on the closed interval AB if there exists a convergent series Mn summation Mn of positive numbers such that for all x belongs to the closed interval AB such that summation of un of x less than or equal to Mn for all n. That means what? For all the values of n, this n term of that series un of x should be less than or equal to capital Mn that. So this is what it is that. So here we have a term by term integration of uniformly convergent series, which requires that only continuity of the individual terms. This condition is almost satisfied in a physical applications term by. So sorry, I will see that in the next slide. Oh, let us see the properties of uniformly convergent series. Now you can see that properties of uniformly convergent series. So uniformly convergent series have three particular useful properties. Very significant properties these are. If a series un of x is uniformly convergent in a closed interval AB and the individual terms un of x are continuous, means what? Each term of that series are continuous. That in the first property you can see that the series sum means what? This summation of un of x we can have, that is, it is a function of x, so which is always continuous. That sum is always continuous. As I told you that each term of that function is each term of that series is a function of x, so that which are continuous, so that that sum is always continuous. And second property of this uniformly convergent series, the series may be integrated term by term. The sum of the integrals is equal to the integral of the sum. Sum of the integrals is equal to the integral of the sum. That it means integration of s of x dx is equal to the summation of the integral of un of x dx. And the last property of this uniformly convergent series, the derivative of the series sum Sn of x, s of x is equal to the sum of the individual term derivatives. Means what? Derivative of s of x with respect to x is equal to the summation of the derivative of x of un of x as n is 1 to infinity, provided the following additional conditions are satisfied. What are the additional conditions? That is, this in this summation, this d of dx of this un of x is continuous in the closed interval AB, and also summation of this d by dx of un of x is uniformly convergent in the given series, given interval, that closed interval. So term by term integration of a uniformly convergent series, which requires only continuity of the individual terms. This condition is almost satisfied in physical applications. The term by term differentiation of series is often not valid because more restrictive conditions must be satisfied. So this is what we have discussed in this video. So one is what is the uniform convergence of a series, and also properties we have seen that, and also non-uniform convergence of series. By taking an example we have discussed that also. These are the references we have followed in this lecture. Thank you.